Today we're going to talk about LeetCode question number 210, course schedule 2. So there are a total of num courses you have to take labeled from 0 to num courses minus 1. You're given an array of prerequisites where each element in prerequisites, A and B, indicates you must take course B first if you want to take course A. Okay, so you need to take, before you take course A, you got to take course B first. For example, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return the order of courses you should take to finish all courses. If there are many valid answers, return any of them. If it's impossible to finish all courses, return an empty array. Okay, so basically this is a kind of a graph question. I'll draw this example out. So we have 1 and then 0, so 0 is a prerequisite for 1, and then 2, 0 is a prerequisite for 2, and 3, 1, and 3, 2. Okay, so basically before you can take course 1 or 2, you have to take course 0, and before you can take course 3, you have to first take course 1 and 2. Okay, so this is called topological sort, where you sort based on the node that when one node points to another node, this node is ordered first. So the least dependent nodes that have no other dependencies to other nodes, they're ordered first. And the nodes that are dependent upon that node are ordered second. Okay, so for this example, topological sort would be 0, 1, 2, 3, or 0, 2, 1, 3. Doesn't matter. Okay, so yeah, so this is how we order it. So if we have a graph where it's a node and children, so let's create a table here that represents node and children. So node 0 and it has 0 children. We have node 1 and it has 1 child of 0. Node 2, 1 child of 0. And node 3, 2 children of 1 and 2. Okay? So if we look at node 0, it has no children. Okay, it means it's not dependent on any other objects here. So obviously in our topological sort, 0 is going to come first. And if we look at 1, it's dependent on 0. Okay, and 2 is dependent on 0, and then 3 is dependent on 1 and 2, so it goes last. Okay. And is there a case where if it's impossible to finish all courses? Well, yes, there is, and that is if we're stuck in a loop. So like, for example, this. Basically, we can't take course 0 until we take course 1, and we can't take course 1 until we take course 0. So we can't take any courses, we're just stuck. Okay? So yeah, this is a good example of topological sort, and the runtime is O of V plus E, where V is the number of nodes and E is the number of edges. Okay, now to code it up. So first one I want to do is create my adjacency list. And my adjacency list is going to contain node and a list of children as an array. Okay, so for I in prerequisites here, if I at 0, remember prerequisites contains 2D arrays, not in graph, and graph I for this key here is going to be equal to a list of just this one element so far. Else, what we want to do is get the children so far for this node. And then add the new elements to children, new child to children, and then reassign this updated children's list to our node here. Okay. So now that we have that, let's define our topological sort here, which is our breadth first search. So now what we're going to do is define our visited set. Sets are all of one lookup time, and visited set. Visited set, that's self-explanatory. If we already visited a node, we already explored it. We don't want to have to explore it again. So we're just going to store that to here to remember not to explore it again. And for visitin, this is kind of important because it shows if a node's status is currently visited, which means that we're doing depth first search on it. We're exploring all its children, and if a child has that visited node as its child, and we see we're already visiting it, then we have a loop. So for example, if we have like this graph here, and we start at 0, then add 0 here, then we're going to add a 0 to our visiting. We're going to start exploring that, and we're going to explore its children. So now we see 1 is its child. We're going to explore that. Remember, this is depth first search. We're going to explore as deep as we can go in the graph. So we're going to add that to visiting. Okay, now we're visiting 1, and let's look at its children. Okay, in its list of children, it has a 0. So now we're going to add that to visiting. But wait, visiting 0 is already in visiting. We're still visiting 0 and doing that first search on it. So that means we must have a loop. Okay. So yeah, that's the main idea with that. And now for topological sort. So for I in range num courses, if I not in visited, then what we're going to do is call our helper function, our topological sort helper function. Sort return empty array. I forgot to initialize my result array here. Okay. And why did I do this syntax? Well, I'll explain once I implement this. And if after all that we never reach this false statement, we never reach an impossible situation where we can't finish all courses, then we return the result array itself. Okay, now let's define the topological sort here function. Going to take a node, and if node in visitin, then return false. Okay, so that's the idea with here. If we're visiting a node already in our depth first search topological sort, then we want to return false straight away. Tell this guy, hey, it's false, and then return an empty array. Okay. Otherwise, if node not in visited, what we want to do now is set this node status to visiting. Now we're visiting this node. Okay, and then get the children of node. So node in graph. Then graph at node here is going to equal, or sorry, children equal to graph node. Okay. And then for each child in children, do that first search on it. So this for Yeah, same idea here. If we know it's false, then just return false. Yeah. Okay. And finally, once all that's done, if we don't encounter this statement here, we don't return false. So what we're going to do is change the state from visited to visited. Is say n.new node visit n.add or visited add node, and then we're going to append our to our result. And then finally return true. Okay. So as we go deeper and deeper into the tree, once we encounter a case where a node has no children, we're going to append, and if a node has no children, that means that it's a node, that is a class we have to take first, because that node can be the prerequisite class for other classes. So we add it first to our list here. And in our recursive calls, we visit all the other nodes that have that single node as a child. So yeah. Okay. Yeah, I'll try running it. Okay. Let me try with other sample test cases. Okay, looks good, and I'll try submitting. Okay, great. Thanks for watching.